Hello, this is Dan Alford. Welcome to the ARC Specialties Weld of the Week. Hello, this is Dan Alford with the ARC Specialties Weld of the Week. Over the next couple of episodes, we're going to be covering the process of welding procedure qualification. No better place to do this than at Welding Consultants LLC, our materials testing lab in Columbus, Ohio. First episode, we're going to talk about the destructive material testing techniques to quantify toughness and tensile strength. And in the second episode, we're going to cover the non-destructive testing techniques, both of which are essential to welding procedure qualification.
Hey, Dan.
Zach, so what do you do for us here at Welding Consultants?
I do both the machining side and the testing side. So at the moment, I'm machining out Sharpies. We usually do them in batches of 10 at a time in the machine.
Is this a Sharpie specimen here?
Yeah, so this is part of the pipe after it's been flattened. It's got the length of the Sharpie already cut, and then I will be facing off the height of the Sharpie. And
so this is the original surface of the part. You're trying to get rid of the surface coatings, the oxides.
right, so there could be a number of different kind of paints or oxides. The idea is to machine off the minimal amount of material, but still have a completely clean machine surface.
And so this was a manual operation back when I bought this company.
Right. Yes, we were working on the manual mill back there, eyeballing everything and just checking what sense. But since we got the Haas here, we then use the wireless probing system. And what it does is it'll, instead of me trying to figure out where that surface is in the space of the machine, it'll just touch off from that surface. And then it knows exactly where that surface is. And it will do a logic check to make sure if it faces off about 30 thousandths or 300ths of an inch of material, that it's not going to hit my jaws that's holding the part. So I can, set the machine to go and go run saws and then come back, and then I've got a clean machine part without having to, crank on any handles or anything like we were.
So with numerical control, we're making them faster and more repeatable.
Absolutely, yeah. Yeah, it takes out the human error for the most part. There's some dialing in that's involved with that, but once you get the work on the front end done, then you're free on the back end to do the other labor.
Explain to us what's the point of a Sharpie test? What are we trying to determine?
See, with the Sharpie test, we're breaking the Sharpies at different temperatures to see the impact toughness at those temperatures. And as we do the different temperatures, we create a curve based on the amount of force that it takes to break the Sharpie. And then you can get a lot of information from that curve and its performance in different temperatures.
So typically, as the temperatures go down, what do the Sharpie values do?
So the Sharpies will have a less toughness from the impact. They will be much lower, and then often you will see that they have a more brittle break.
So you're determining what the acceptable service temperatures for any given part are.
Right, to the best of our ability. Sometimes with the welds and such, you'll see some irregularities, but base metal is very consistent in that sense from what I've seen.
We'll start it up.
All right.
What's the first operation?
This is our probe in here. It's checking a spot where it knows that there won't be any girth weld that it could possibly hit and give it a bad reading on the surface of the pipe. It then goes to a prompt here. It's done its logic check. It knows that if I hit to machine it, it's not going to hit the jaws. I got to tell it how much to take off. Since this is a base material Sharpie specimen, then I can say, take off to the size from the get-go. I don't have to do multiple passes for this one, so I'll hit B here.
So this is one of your programs?
Yeah, I've been working on this one for a while. It's when we got the probing system, it unlocked the macro variables in the controller. And once you're able to program with the macro variables, it opens up a lot of automation and options for you.
pretty confident what's going to make a good part.
I've let it run a few times now. Yeah, when we first get the machine, like any program, I'm sitting here with my finger on the red button, ready for something to happen. But once you prove it out and you've run it so many times, you got that confidence. And I won't even be in this room sometimes on a lot of my programs because I just understand what's going to happen at this point.
So the part's ready?
Yeah. So in the case that it was not ready and there was some unclean surface there, I can have it loop back and continue the same way as before. But since it is finished, then I'll hit the end button and it will bring it to me.
What's the next operation after this?
Next operation is engraving. So they're in a brick of 10 at the moment. So I'll take it over to our inventor, and basically what it will do is it'll separate with lines as a guide the 10 individual Sharpies, and then we will also engrave the specimen ID on the side of the Sharpies.
Both ends?
Yes, both ends. So then, once they're broken too, you're not trying to put 1 and 2 together.
Makes it traceable.
That's right.
And then you part them into 10 pieces.
Right. Then after that, it comes back to the machine. We're doing Sharpie width, which is a lot more complex. It's got a finishing operation that has a 2,000ths tolerance. So that's where our finisher with the wireless tool setter comes in, because in the program we have it set to check the surface of the surfacer's teeth every time it runs the program in case there's any wear. Because 1,000th of wear, when you run one side, flip the other, you're doubling that air.
Right.
So I got to check it every time.
And then there's one more operation. The grooving?
The notcher, yes.
Notching.
Yes. We've come up with our own method of notching that I've enjoyed a lot with our notching tool in our carousel here. And basically, with this tool, it's an unconventional way of making a notch. It's actually meant to do other jobs, but to mass produce these, we have to set the Sharpies at a very specific angle that coincides with the tool, so that the two angles line up and we get a very perpendicular notch that's very repeatable every time.
From my understanding of Sharpie testing, that notch is so critical for repeatability in your results. Is that the case?
Absolutely. We're constantly checking the notch tool. We have an idea of when it's even starting to become dull in the slightest based on the feathering of chips and stuff. And as soon as it becomes questionable in any way, we start switching out inserts, reprobe the tool, make sure everything's back the way it should be. Because once you check those notch, there's no putting the notch back and redo them.
Fascinating. And then after you finish with them, they go to the Sharpie machine for actual testing. Excellent. Well, thanks for the explanation. So we saw Zach cut the specimens for impact toughness testing. Now we're over here working with Casey to actually test the specimens. Casey, what's this machine here?
Well, this is our Sharpie V-Notch impact toughness tester. And it will measure the impact toughness of the materials that we place inside it.
So what's the calibration routine that you go through before you break a specimen?
Well, it's called a free swing test. And the first step is to let the machine swing freely without a specimen loaded in it. And then on the 6th forward, we will push the needle back forward, and it should read between 6 and 9.
What's that check out?
It's checking the friction and windage loss of the actual machine.
Demonstrate.
All right.
So it went to 0, is that correct?
That's correct.
It's 3, 4, 5, 6, so that was the friction and windage loss.
That's correct.
Okay. So once you calibrated the machine or confirmed calibration, what's the next step?
Well, the next step is to reset the machine, and then we can begin testing.
So temperature has a big effect on Sharpie toughness, right?
That's correct.
So what are we testing at today?
Well, today we're testing at about 100 degrees Fahrenheit. And
Why 100? I've not heard testing at these temperatures, at this high temperature.
well, for this particular customer, we're identifying the upper and lower shelves of the shear area. So they might not specifically know exactly what kind of properties the pipe that they have in service is. So they've used us to identify that.
So this is an older pipeline.
That's correct.
So we're trying to figure out what they used back in the day.
That's correct.
Okay, so you've got these specimens heated to 100 degrees Fahrenheit. Are they ready to go?
They are right now?
Okay, can you demonstrate this?
Certainly.
Ten foot-pounds, that's low, right?
That is kind of low, but they are also sub-sized specimens.
So these are not the normal, what's the normal dimension, 10 millimeter?
10 millimeter by 10 millimeter.
And these are thinner, why?
Well, the pipe thickness just doesn't allow for a full-size bar.
So you can change that thickness and you have a ratio that you can calculate.
That's correct.
So is this an acceptable test or unacceptable?
Well, we're not testing for acceptability or unacceptability. We're just identifying materials.
Just characterizing parts. Okay, so we've broken the sample, we've determined the energy absorbed was 10 foot-pounds. Is there anything else you learned from this test?
Well, we can also get some extra data out of it. We have lateral expansion and shear area we can report.
So how do you do shear area?
Well, shear area is a visual estimation. We take a look at the bar and we're looking at the grains that are present or not present, and that determines if we're at the upper or lower shelf of brittleness.
And then what was the third inspection criteria you're talking
It's
about?
called lateral expansion.
And how do you measure this?
Lateral expansion is used with essentially a dial indicator, and where we're measuring how much deformation the bar took when it was struck by the impact tester.
The greater the deformation, the higher the toughness.
That's correct.
So tensile testing is one of the most important destructive testing techniques. So Zach has cut and prepared these specimens. We clamp them into the machine. He's installing the extensometer, which actually measures the amount of strain or elongation in the part. Preloading the part now to get the extensometer preloaded. Then he'll zero this out. All this occurs before we do the actual tensile test. So Zach, we ready to run this test?
Yeah, we're ready.
Show us how it works. So we're applying a tensile load to this specimen at this point, developing the stress strain curve.
At the very beginning, yeah, you'll start, this is where you'll see if your fixed string is solid or not, because you'll see slippage if it's not. We got a pretty good hold right here. So then we'll start seeing a slope here shortly. We have I don't know what it is off the top of my head, but we have a specific velocity that we have to pull the tensile at, or we cannot go past that velocity, I guess is the best way to put it.
You know, velocity affects the mode of failure.
Right.
So what's our tension at this point?
Right now we're seeing about 6,000 psi, which for this part is about 2,500 pounds. It's still in the low part of the slope. We haven't gone too far yet, but it is seeing quite a bit of load at the moment.
So we're still in the elastic range. We haven't reached the yield line.
That's right. If I stop the test right now, that part would be just fine. It would spring back to the original state.
How far is it elongated at this point?
It should not have elongated the part at all, but the actual strain we were reading about 0.005 of an inch.
So it's barely moved at all.
Yeah, you couldn't see it with your eyes at this point. It's just our sensitive extensometer there. So it looks like our slope is fair to top out, and what that is we're getting past the point of plastic we're getting to the point of plastic deformation. If I stop the test after that, the part's not going to return back to its normal form.
You've stretched it permanently.
Yes. Yes, as it's flattening out, you'll see here. That's after that point when it starts flattening out, you'll then be able to start seeing physical deformation in the part with your eyes at that point.
And we can't take this to failure with the extensometer in place.
Yeah, preferably not. The extensometer is a very high-tech piece of equipment. We don't want to trash that with the part breaking. It can be a violent break, or it could be, a weak break, depending on the material and the strength.
What test are we conducting right now? Are we trying to characterize an unknown steel, or are we testing a known steel? What's today's exercise?
So this is a base metal, and what we have is a transverse base, so transverse to the axis of a pipe that's been cut out, and it will be compared to a transverse weld, a weld that runs axially through a pipe, and that weld will be right in the center. I run those back to back, and we compare the data that way.
So this simulates the hoop stress from pressure inside a pipe.
That's right. And it's actually prompting me now to remove the extensometer because it has reached...
It's reached the yield point?
Yes, we're completely flat now, so I will no longer be reading the elongation. Now we're just getting that maximum stress for failure.
And about how far did it stretch?
At that point, we were about 6/1000ths.
Only 6/1000ths?
Yes. Right here is where you see major elongation. It can be 1/4 inch or more.
And that was over a 2-inch gauge length, or what's that?
Yeah, 2-inch gauge length is what we measure across.
But now I'm seeing stretching on the order of a 1/4 inch or more.
Yeah, it's hard to tell at the moment, but this is definitely stretching by quite a bit. You can tell physically that is not 2 inches anymore between those two marks.
So that's one of the other things we're measuring, right, is elongation and reduction of area.
That's right. As it gets pulled apart and that elongation is happening, the center of the tensile is actually getting smaller in its cross-sectional area, and that's how we get that pounds per square inch.
So we're actually, this will give us, there it went. That gave us some determination of ductility. We saw decent elongation and good reduction of area. So this is not a brittle part at all, is it?
That's right. This is one of the more ductile parts I've tested.
Thank you very much.
Thanks, Dan.
I hope you enjoyed our episode on mechanical testing, where we demonstrated how you measure yield strength, tensile strength, ductility, and toughness of welded joints. In the next episode, we're going to cover non-destructive testing, including ultrasonic testing, liquid penetrant, and magnetic particle. If you need assistance with welding procedure qualification, contact Matt Brinkman at Welding Consultants LLC in Columbus, Ohio. We look forward to posting new episodes of the ARC Specialties Weld of the Week. If you're one of the thousands of operators of ARC Specialties equipment around the world and you have a weld that you would like to showcase, please contact us. At ARC Specialties, we thrive on problems. Send us yours.